Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us for this video. We're continuing to look at digital logic gates, truth tables, and Boolean expressions. And in this video we're going to look at DeMorgan's properties for Boolean expressions, both the and the or version of those. If you haven't watched the first two parts of this Boolean simplification video sequence, then I might recommend that you do that first so that you have some of the background that we will be using in this video. Let's get started. So before we go any further, I want to take a look at this resource here that I should have shared, I think, earlier, but that's okay. You guys can take a look at this. I want to highlight the things that we've looked at so far. So we've looked at the identity for the and, which says that anything anded with one is just going to be itself. The one just says, hey, that other thing is what you're looking at. And then we looked at the complementation for the or, which says that if you or it's something with the inversion of itself, you're always going to satisfy that, so you'll always just be a 1, so that turns into a 1. We also looked at the distributive property, and we looked at this one here, the and version of this. And we looked at the absorption property for the or, and we looked at the consensus property for the or. Today we're going to look at the DeMorgan's and or, and we're also going to encounter the double inversion with also a few of these other ones in the basics. I want to quickly talk over these basics. They are pretty intuitive, but it's good, I guess, to look at them once at least. And so the annihilator terms in and or, basically they become either a 0 or a 1, so they annihilate any of the term or literal that is in the operation. And so if you have anything anded with 0, that's already, the 0 disqualifies that, makes it false in an and situation immediately. And so anything anded with 0 is going to be 0, so the thing was annihilated. And same thing on the or side, except or is very permissive, so anything or with 1, well, the 1 satisfies the expression, so it'll become a 1, so that anything doesn't matter. So anything ordered with 1 will just become 1. Okay. We looked at the identity on the and side. If you and something with 1, the 1 just says, okay, I'm done, I don't really matter, and so just look at the other thing, and so it becomes itself. So x and 1 is just x. On the or side, if you have a 0, the 0 is not going to satisfy it, but so you just look at the x, so the 0 has nothing to do with it. So x or 0 is just x. Then we have this idempotence. Idempotence just says that if you and or something with itself, it just becomes itself. So x and x is just x, and x or x is also just x. And then we look at the complementation for the and side. On the or side, if you have x or its inversion, you're always going to satisfy that. So if x is 1, then the inversion is 0, but you're oring it, so the x is 1, so that's good. If x is 0, then the inversion is 1, and since you're oring it, you still satisfy that. And so it's always going to be 1. Similarly, analogously, for the and side, if you and x with its inversion, one of those is always going to be 0, and if you have a 0 in an and situation, then the overall output is 0 as well. So those are all the basics there. The commutative and the associative, I pretty much ignore, but basically all that says is that you're able to move terms around inside the expression. And you're able to evaluate different parts, either earlier parts or later parts of the term, and it doesn't affect what the outcome is. So I don't make my students do these and write these down and say, hey, I did an associative, or hey, I did a commutative, because I find that to be tedious. And my experience is that all my students do this properly, and it's not an issue. So we're just going to focus on the other ones here. So yeah, some of these I didn't look at, and I would leave that to you to do it if you want to specifically. So I highlighted the ones that I think are more accessible and also that are used more frequently in this type of simplification that we do in our typical Introduction to Digital Electronics class. Hopefully you found that useful. Let's go ahead and move on to DeMorgan's. DeMorgans. If you're familiar with Stranger Things, you know, I don't know, that came out when I was teaching this class, and some of my students called it the Demogorgons. Oh, are we using Demogorgons rules? You know, so I just thought that was funny. Thanks for listening. So DeMorgans, there's a little catch phrase that goes with this. It's break the line, change the sign. And so essentially what we're going to look at in DeMorgans, so here's the and version of it. The and version of it looks like this. If you have a term, and I call this an overbar, and so if there's an overbar of the whole term, so this is a little bit different than having each literal have a bar over it. So this is, for instance, not equal to x bar, y bar. So this is a common mistake that students do, is that they look at that and say, oh, x, y bar is x bar and y bar, and that's just not true. So what is x, y bar? Well, the DeMorgan's theorem says that x, y bar is equal to x bar or y bar. And so what did we do here in terms of break the line and change the sign is that I sliced this line in two to get 2 bars, right? And then I changed the sign in between here from an and to a or. And so x and y bar, for some reason now I don't like this, so I'm just going to go ahead and take that away. And so x and y bar, quantity bar is x bar or y bar. So that's DeMorgan's for the and case. Let's do an example. So I have f is equal to x, y bar and y. Okay, and so we take that x, y bar, break the sign, change the sign. We got x bar or y bar. So that's that DeMorgan's. And that's still going to be ANDed with y. And then I can distribute y, and so we'll have y x bar or y y bar. And so this is distribution. And now I notice one of those basics, right? So y and y bar, with itself. So this is complementation. So one of these is always going to be 0. And so we have y x bar or 0. This is complementation. Now we have something ORed with 0. So something ORed with 0 is just going to be itself, and this is identity. And then we end up with our final answer, y x bar, or if you'd like to put it in alphabetical order or input order, probably f is x bar y. So that's how we sort of unboxed or uncovered or released this overbar. See, the overbar kind of traps the literals underneath it, and so we can use DeMorgan's to get these literals by themselves, and then we can continue to do our distribution and stuff like that. So as long as there's an overbar, you got to treat that as one package, and you can't break that apart until you've done a DeMorgan's or a double inversion or something like that to get out of it. So you just got to be aware of that. Okay, so let's go ahead and look at the OR version. So the OR version is x or y bar, right? And so break the line, so split that in two. So we got x bar and y bar, and then you change the sign from an or to an and. So this is the OR version that we're looking at. So let's do an example. So we have f is, I'm going to make this one a little more interesting. So we have this whole term underneath this bar, and there's an OR there that connects these two pieces together. and that's going to be OR with y z bar on the outside. So I'm going to do DeMorgan, and so we'll do that right here. Now I want to treat this piece here as two things, right? Because we have x or x or y. So one of these is x and one of these is y, if you will. So I'm going to kind of define A as x, y bar. And so we can think of this as A or z barred or y z bar. Okay, so I've turned this into one package. Now you don't need to do this if you can see it, but I think it's a good way to kind of understand what we're doing here. And then we'll resubstitute back in for A a little bit later. All right, so now this looks exactly like our definitional DeMorgans for OR, and so we can make that exchange there. So it's going to be, A bar and y, or sorry, what am I doing? I'm writing down the definition. Let's do that again. Cut, take two. All right, we got A bar and Z bar, or Y Z bar. And so this was DeMorgan's right here. Perfect. So what's next? So let's substitute back in now. So now we have x, y, bar. Lots of bars. Right, so what do we have to do here to get rid of that overbar? That overbar on two ANDed literals. Well, we do DeMorgans, and so this becomes x bar or y double bar and z bar or y z bar. So this is DeMorgans. Okay, so we split the sign, ended up with a double on the right, ended up with a single on the left, and we split the line, and then we changed the sign to an OR. So this is where we have the double inversion. So y is double inverted, and so when we take care of that y, double inversion just becomes the original y, and so this is a double inversion. All right, so now let's distribute the z here. So we have x bar z bar or y z bar or y z bar. And so this is distribution. Okay, and then we can see that these two terms are the same. So we have y z bar and y z bar, and so if this is what we would call idempotence, and so if you have y z bar and or y z bar, it's just y z bar. So this is going to be x bar z bar or y z bar, and this is idempotence. And I think we're done. Oops, I forgot the bar here. You could distribute the z bar, but that doesn't get you anywhere. And so there we have our final answer. All right, so that looks more like an example simplification that you might see in a problem where you have a couple of steps to get to the end. But I just want to show you that DeMorgan's is a powerful tool. It shows up, and you have to know how to use it properly. We also want to take care that when we have a term underneath a bar, we have to keep that term together and do the inversion on it as a whole. And so that's why we brought that A sort of intermediate substitution in there to allow us to see that happening. I hope you found this to have value for you. I hope you enjoyed it, and we'll see you next time. I'm Mike Stanzik, and this has been Digital Electronics Classroom. Have a great day.